Hi all, welcome to part 5 of Neurons 2. Let's continue talking about the action potential. The action potential is all or none. And what does that mean? Well, if you have a graded potential that's below threshold, no action potential is going to happen. Correct? We talked about that. But if it does reach threshold within that cell body, reaches the axon hillock or the trigger zone, it will reach the axon terminal. It'll arrive at the axon and go all the way to the very end of the axon terminal. It will not peter out halfway and not reach its target. Okay, so that's what we mean by all or none. None means it stays on the cell body, never triggers an action potential. All means it gets to the very other end of the axon. There's no stopping halfway. Let's compare one more time those action potentials and the graded potentials. The action potential travels long distance along the axons. The graded potential remains local on the cell body. It could also remain on the dendrite. The action potential does not diminish in strength over distance, but the graded potential can fade away over distance and not reach the axon hillock. The action potential always is of the same magnitude. It either gets up to that plus 30 millivolts or it doesn't. So it's of the same magnitude. Whereas the graded potential can be of a variable magnitude depending on the strength of the stimulus. If the mosquito lands on you, that's a very small stimulus. If the hammer lands on your hand, then that stimulus is way more intense. And we're going to talk about how those look at the physiological level. Action potentials are voltage gated mostly. And graded potentials, you can tell me, what could they be? Chemical or mechanical, you have a neurotransmitter. So voltage gated on the action potential as it travels along the axon. Voltage is going to stimulate the neighboring section. But graded potentials are coming into the cell body through a neurotransmitter. Okay, if all action potentials are alike, what makes one signal stronger? So here's my little stick guy, and he's now lifting something up that's very heavy. So this signal coming to his muscles, it's got to be an intense signal. It's got to be saying, put lots of strength into that because I'm lifting something very heavy. But I'm telling you that all action potentials are the same. They go to plus 30 millivolts and back down again. So how is it that you regulate that? So what we're talking about is stimulus intensity. It's got to be a more intense signal coming to muscles when it's something that's more demanding. It turns out that graded potentials produce not just one firing, but many. They produce bursts of action potential. So you'll have go, or maybe go. You have these different bursts of these action potentials. And the amplitude of that graded potential, in other words, how strong you want that response to be, is going to be determined by the frequency of the action potential. So if it's go, it's going to be different from go, correct? So it's the frequency. Now, what does that do? What does an increased frequency create? An increased frequency creates a greater release of neurotransmitter. So if you have more neurotransmitter released, it's going to be a more intense signal. How did you get more neurotransmitter? You did it because you delivered those signals more frequently. I hope that's clear. In this slide, I'm showing you something super loud in your ear. This is intense, right? It's of great amplitude, which means the frequency is coming into your ear really fast. Okay, I'm sending action potentials in that eardrum very quickly. And I'm releasing a lot of neurotransmitter. And I'm hearing a big loud sound. Let's look at the same concept then in graph form. This is a membrane potential in millivolts. We start at minus 70, and let's say you have a small release here. These numbers are wrong. This should be a minus 30, but this doesn't reach threshold. Here we have them reaching threshold. So threshold, 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 4 of them. And given that they have all created an action potential, we have here, let's do this with my pen. We have little balls of neurotransmitter, and I have 4 of them here. That's how much neurotransmitter release I had when I had an over the threshold response or stimulus given with this kind of frequency. Now let's compare that. Let's compare that to, again, membrane potential here. This is the graded potential coming of different intensity. This is the action potential reaching threshold. This action potential is much more frequent. The outcome here is that I have more neurotransmitter released. More neurotransmitter is a more intense signal. So it has to do with how many of these action potentials are reaching threshold within a certain period of time. This is some more information about sodium and potassium channels, the velocity of response. How quickly can they do it, right? If we're talking about frequency, we want to know how quickly. So sodium channels open rapidly. As soon as they get the signal, the sodium channel opens. Potassium channels are slow to open. So they get the signal at the same time that the sodium channels get it, but they are slow pokes and they will take longer to open. That's why you have depolarization here when sodium moves and repolarization when potassium moves. What else? Think of that transmission of an action potential kind of like doing the wave, right? Because the action potential is going to open channels here and then open channels there and then open channels there. And as it goes along, it goes stimulating through voltage, stimulating voltage-gated channels in the vicinity. It's kind of like a domino effect that will travel all the way down the axon. In this picture here, it's sort of traveling down but hasn't quite yet gotten to sections 10 and 11 here. Okay, it's kind of like the wave. Sodium channels in the axon have 2 types of gates. They have an activation gate that's going to open it and allow those ions to move, and an inactivation gate. It's going to be a gate that stops it and stops it from going backwards also, and I'll talk more about that. Here we have the membrane, a sodium channel, and it's a model for you to see. This would be an activation gate. And we're going to make a little ball and a string be an inactivation gate. So if this is closed here, if the activation gate is closed, the sodium cannot come into the cell, and off it's going. Do you notice this is sodium out here? There's a lot of sodium. It's wanting to come in. It can't come in because it's going to bump here and shoot back out again. So it can't come in unless I open the activation gate. Once you get a depolarizing stimulus, it's going to stimulate this channel. That channel then is going to open that activation gate, and sodium is going to be able to come in, right? And this is the inactivation gate that's just sitting there. So if I go to my graph, I would be minus 70, and now I've reached that depolarization. It's reached the minus 55. It's going to keep going up here, but for now I have sodium coming in. That's their picture of the sodium entering the cell. So here in my chart, this is climbing, more sodium comes in, more of this is going to climb, correct, till about minus 30. until I close it up again. But let's see that in the next slide. This activation gate takes a while to shut back up again, right? Remember, this is all a model. It's really molecules that are changing shape. And when that molecule changes shape, then it's going to find itself in an orientation that doesn't let the sodium in anymore. But we're just drawing it as if it was a stick in a ball. So the stick here is now open. That region is opening, but a different portion of the molecule is able to plug that entrance. It doesn't allow, because of the change of shape, it doesn't allow the sodium once again to come back in. So that region of the molecule, we're going to call it the inactivation gate. And then sodium can no longer go in. Once the activation gate is ready to reset, then the inactivation gate changes shape again, and then this can come back. So now I've reached the plus 30. The two gates reset to their original position. Who cares about this? It's like, so what? Well, these gates are going to prevent backflow. Without the inactivation gate, the channel would stay open longer. It would allow more sodium in, and there'd be no time to stop that channel. And if you don't stop this channel, once the next one is already firing, let's make another one here, and the next one that's going to be next there, and this one's still firing, everything behind it will still be active. And in that case, it's not moving, but it's either staying active or actually shooting backwards. So what we need to do is inactivate that channel, not once it's done its thing, once it's passed it on to the next one. Inactivate it, let it not be stimulated for a little bit, so as to allow this flow to be in one direction only and not shoot backwards. That's the rest period. I'm going to stop you here. We'll talk about myelin next. Let me go back to this slide for a little bit and make sure that you understand this. This prevention of backflow is what's going to allow axons to have their current travel in one direction only. Okay, let's stop there. Thanks, guys.